Imagine you throw a book into a black hole. Not just paper and ink, but every word, every sentence, every idea contained in that book. Where does that information go? According to Stephen Hawking's groundbreaking 1970s calculations, the black hole will eventually evaporate away into random thermal radiation. And the information from your book? Gone forever, erased from the universe. This idea directly contradicts one of the most sacred principles in all of physics: that information cannot be destroyed. Quantum mechanics says the past should always be reconstructible from the present. Hawking said, "Not if black holes are involved." This clash is called the black hole information paradox. And for nearly 50 years, it has been the greatest unsolved puzzle at the intersection of quantum mechanics and gravity. Welcome to Großdenken, everyone. Today, we are going to explain exactly what the paradox is, why it matters, and the leading ideas that might resolve it. Please support this channel by just subscribing. That would mean a great help. Here is the setup. In 1974, Stephen Hawking combined quantum mechanics with general relativity near a black hole's event horizon, the point of no return. He showed that pairs of virtual particles constantly pop into existence. Normally they annihilate instantly, but at the event horizon one particle falls in and the other escapes as what we now call Hawking radiation. This radiation carries energy away. So over an incredibly long time, many times the current age of the universe, the black hole evaporates completely. But here is the problem. Hawking's calculations showed that this radiation is thermal, completely random, like the glow of a hot coal. It contains no information about what fell into the black hole. If the black hole evaporates entirely, the information from your book and everything else that ever fell in is gone forever. Why is this such a big deal? Because it pits two pillars of physics against each other. Quantum mechanics is built on unitarity, the idea that quantum information is always preserved. The wave function of the universe evolves in a way that is reversible. You can, in principle, run the clock backward. If Hawking was right, then pure quantum states can evolve into mixed states, a loss of information that quantum mechanics says should be impossible. Hawking himself argued in his 1976 paper that this meant physics loses predictability. That is the paradox. Two incredibly successful theories, general relativity and quantum mechanics, give contradictory answers when you combine them. Something has to give. The debate became so intense that in 1997, Hawking and Caltech physicist Kip Thorne made a famous bet against Caltech physicist John Preskill. Hawking and Thorne bet that information was destroyed by black holes. Preskill bet that it was preserved. The prize? An encyclopedia, from which information could be recovered. In 2004, Hawking famously conceded the bet. He announced that he had changed his mind, admitting that information can escape from black holes after all. But here is the catch. Hawking conceded without providing a full mechanism. He admitted the paradox existed, but the solution remained and still remains elusive. So, how might information escape? Several ideas have emerged. Idea 1. Soft hair. In 2016, Hawking, along with Andrew Strominger and Malcolm Perry, proposed that black holes are surrounded by zero-energy particles called soft hairs, photons or gravitons that can encode information about what fell in. As the black hole evaporates, these hairs could carry information out. Idea 2. Fuzzballs. String theorists like Mathur argue that black holes are not empty voids with a singularity at the center, Instead, they are fuzzballs, gigantic fuzzy strings that have no event horizon at all. If there is no horizon, information never gets trapped. It can leak out naturally. Idea 3. Quantum hair. Recent research by Xavier Calmet and Stephen Shu suggests that the quantum state of the graviton field, the particles that carry gravity outside the black hole, carries information about the interior. The no-hair theorem only applies to classical gravity. Quantum gravity may have plenty of hair. The common thread? All these resolutions require going beyond Hawking's original semi-classical calculation. They require a full theory of quantum gravity, which we do not yet have. The paradox has also spawned an even more disturbing idea, the firewall. In 2012, physicists including Joseph Polchinski argued that preserving information might require a wall of fire at the event horizon, incinerating anything that falls in. This would violate Einstein's equivalence principle, which says free fall should feel like nothing. Meanwhile, experimental physicists are now building analog black holes in laboratories, using fluids, sound waves, or ultra-cold atoms to simulate black hole horizons. These experiments cannot resolve the paradox fully, but they can test specific predictions about how information might escape. The honest truth? After nearly 50 years, the black hole information paradox is not solved. We have promising ideas: soft hair, fuzzballs, quantum hair, but no consensus, no experimental confirmation. So what is the black hole information paradox? It is the collision between quantum mechanics, which says information is eternal, and Hawking's black hole calculations, which say information can be destroyed. For nearly 50 years, the greatest minds in physics have wrestled with this problem. Hawking himself changed his mind. But a full resolution will likely require a complete theory of quantum gravity, something we are still searching for. The black hole information paradox is not just an esoteric puzzle, it is a stress test for the laws of physics. Whatever resolves it will change how we understand space, time, and reality itself. Thanks for watching. If you want more deep dives into the universe's biggest mysteries, hit subscribe.